Okay, now we know how to find the general solution to x prime equals px, where p is a constant coefficient, a square matrix. What we now want to do is talk about solving initial value problems using these systems of linear constant coefficient differential equations, homogeneous ones, as our sort of the differential equation that we're going to use. We're going to toss in some initial conditions, which are going to allow us to pin down the values of those constants like C1, C2, and C3 that we see appearing in the general solution. So, truth be told, I was thinking of doing this for the 3 by 3 case, but I think it's going to be too hairy if I do that. So rather, I'm going to go back to the 2 by 2 system that we did in the first video, 2 videos ago, and we're going to apply an initial condition to that. So I'm looking at this guy right here, this one, okay, and I'm going to duplicate it and bring it down here. Oh gosh, how am I going to do this? I have to bring it to a clear space. This is exciting. Adventures in iPadding. Here we go. Okay, so there's my differential equation. I just want, oh gosh, and I wrote the solution up there. Okay, but before I write down the general solution, let me specify the initial conditions that we want to work with. So the initial conditions are going to be a specification of x1 and x2 in this case at 0. And we'll say that x1 of 0 is, oh, I don't know, how about -3? And x2 of 0 is going to be 9. I'm just making things up, okay? I mean, I'm not totally. I have a reason why I chose these particular numbers, but whatever. I don't like lying to you for some reason. I should just pretend that, just lie to you because, you wouldn't know the difference. I want to bring down the general solution, which is sitting right here. I'm going to duplicate this as well. And I'm going to bring that down. More adventures in iPadding. Oh gosh, and I don't know what I'm carrying with me. I'll have to do some erasing. I'm not very efficient at this, I've noticed. Uh-oh. Undo? Oh, good. Look. No, undo. Oh gosh. This is not what I intended. Undo. Okay, let's do this again. This is like humiliating. Okay. I'm gonna take all that, we're gonna duplicate it. We're gonna be good about this. We're gonna touch very gently. Okay, there we go. Okay, exciting. This is our general solution. Okay, and I'm gonna recolor it. I'm gonna make it green. Okay, this is our general solution. And what we want to do is find the x1 and x2, sorry, the c1 and c2, which makes this x further satisfy the initial conditions. Now, let's think. Remember that x1 and x2 are the entries of this vector x. So we could rewrite or recast this initial condition here, these initial conditions, as x of 0 being equal to the vector -3, 9. Okay? X of 0 is -3, 9. So, using that and using this general condition here, the general solution here, we can try to figure out what C1 and C2 are. So if I do this right, I'm going to get a -3, 9 is equal to x of 0. But x of 0 is what I get by sticking t equal to 0 into this general solution here. If I stick t equal to 0 in, what I get is c1 times 1 -1 plus c2 times 1 2. Okay? Now what I can do is compare entries on the left-hand side and on the right-hand side. These are each 2-by-1 matrices. So I can set the entries equal to each other. And that gives me two equations in two unknowns. Watch. I get -3 is equal to c1 times 1 plus c2 times 1, rather. That's just me looking at the top row of these of all these vectors here. And then for the second equation, I get that 9 is equal to negative C1 plus 2C2. Okay? Now, I know you know how to solve this. You learned how to do this maybe in 8th grade or whatever, 11th grade maybe. But we can use the technology that we've just learned about to solve this. And that's kind of what I want to do, because this is a system of linear equations. It's got a matrix bit here, this bit right here. So there's a matrix 1, 1, negative 1, 2. 1, 1, negative 1, 2, which when multiplied by the vector containing C1 and C2, this is equal to negative 3, 9. Okay? So we can solve this linear system for C1 and C2 using matrix methods. That's what I want to do, I guess. I want to do that. So how am I going to do it? Well, I'm going to write down the augmented matrix for this system. That's going to be 1, 1, negative 3, and negative 1, 2, 9. Now I'm going to do row ops. So I get 1, 1, negative 3. I'm going to add row 1 to row 2. And I get this. This isn't so painful. Then I'm going to multiply row 2 by 1/3 to get this. And then I'm going to add negative row 2 to row 1. 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 Okay? And then I can reinterpret this as a linear system. And what this is telling me is that C1 is equal to negative 5 and C2 is equal to 2. So the solution, which satisfies the initial condition, is x equals negative 5 times 1 negative 1 times e to the 2t plus 2 times 1, 2 e to the 5t. How did I do that? I just put C1 and C2 in right here and right here. The C1 and C2 I found. This is how you deal with initial conditions. Okay? Not too bad, right? Good. That's enough. So long.